Hi, and welcome to this section of the Advanced Calculus 2 tutor. And in this section of the class, we're going to cover a topic that everybody studies in calculus and a lot of people have problems with, and that section is called L'Hopital's rule. So if you look in your book and you look at the title of this class, this title of this section here on the screen, it looks like it's L'Hopital's rule, and so you might be tempted to call it that, but the actual pronunciation is a French guy, and so you pronounce things a little differently, and it's called L'Hopital's rule, okay? So it's named after the person that discovered it. It's really cool, but the good news is it's really easy once I explain it to you. Let me give you a little bit of background, a little bit of motivation. Way back at the beginning of Calculus 1, usually the first thing you study is limits. They go into excruciating detail about limits, even before you talk about a derivative. Now, my calculus DVD doesn't start off that way, but most of the textbooks do. And usually in that section on limits, there's a bunch of limits that you have no way of figuring out the answer to, because usually you've got a limit of something over something else, and when you evaluate it as you go off to infinity, usually they're asking you to evaluate something as you go to infinity, okay? You get infinity on the top of the fraction and infinity on the bottom. Usually it's something like this. And so you have no idea what to do. And way back at the beginning of Calculus 1, because remember, this is like the first section of Calculus 1, they usually devote pages and pages of proofs and drawings to show you why this limit converges, okay? Well, it turns out L'Hopital's rule could do that limit in 2 seconds. Okay, it's really powerful and it's really easy. So really the bottom line big picture of what this section is going to be, it's going to teach you a method to evaluate limits that aren't so easy to evaluate just by plugging in the number, okay? And it's going to be really easy. So let's get a little bit of motivation for you here. Let's do some limits that I think you can do. Okay, what is the limit of, let's say, x approaches 0 of the limit 1, or of the function 1 over 2 plus x. Okay, this is not a trick question. I don't have trick questions in this class, so just look at it and tell me what you think. You have 1 over 2 plus x. If you approach 0, if you take x and you approach 0, then eventually this little position here is going to become 0, so 2 plus 0. So it's just going to be 2 on the bottom, right? So this limit is just 1/2 as x approaches 0. That's something that you learned way back in the beginning when you learned what a limit was, okay? So that's easy. Now what if you have a limit, limit of x approaches 0 of something like x over x squared? Now, okay, your first thought would be, well, let me go ahead and plug in x. So I've got x on the top, so I'll put 0 on the top, x squared on the bottom, I'll put 0 on the bottom. So what we say is this has the form of 0 over 0. Okay, because when you put x is equal to 0 in the top, you get 0, and when you put x is equal to 0 on the bottom, here you have 0 squared, that's 0. So 0 over 0, what does that evaluate to, I ask you? What does that evaluate to? 0 over 0. How do you do it? Does the 0 on the top trump the whole thing and make the whole thing go to 0? Because when you have a fraction, anything on 0 on the top will make it go to 0. Or is it go off to infinity because the bottom is 0, so you're dividing by nothing. So what wins, okay? So you really don't know how to evaluate this. You don't know, you don't have the mathematical tool bag yet to figure out how to do that. We're going to tackle these kinds of problems in this section. Let me ask you one more question. What is the limit as x approaches infinity of 2 to the power of x over x squared, okay? So, again, what you want to do is you want to take infinity, because x is approaching infinity, plug it in here. Okay, so what you're going to have is 2 to the infinity power, right? And then on the bottom you're going to have infinity squared. So those are both big numbers, right? So you're going to say it's still the same form. It has a form of infinity over infinity. Because 2 to the infinite power is infinity. And certainly if you take infinity and square it, you're still going to get infinity. So you have the same problem here. You have infinity over infinity. You have some ratio of infinite numbers. And how do you know what this limit converges to? Does it converge at all? Okay. So here you have what we call two forms that you really don't have anything in your bag of tricks to go off and figure out how to do those, because they involve ratios of 0, 0 over 0, or infinity over infinity, and you just don't know how to do that. Let me give you one little teaser of what's coming up, and then we're going to jump right into L'Hopital's theorem, which is going to show you how to solve problems like this, and they're going to be like this, piece of cake problems, no problem at all. That is the following. Now notice that when you go off to infinity, let's say here, 2 to the infinity power, okay, and you have x squared, so you have infinity squared, okay? We know that they both approach infinity. The top approaches infinity by itself, and the bottom approaches infinity by itself, because x is marching towards infinity. So the top is going towards infinity and the bottom is going towards infinity. But these are different functions. So, and this is crucial, listen to this. Even though the top approaches infinity and the bottom also approaches infinity, that doesn't mean that they approach infinity at the same rates, you see. One of these functions could approach infinity much, much faster than the other one, okay? For instance, infinity to the infinity power is going to approach infinity a whole lot faster than infinity squared, right? Because, I know you're kind of stretching your brain here because we're talking about infinite numbers, but when you raise something that's infinite to an infinite power, it approaches infinity much, much faster than if you would just square that infinite number. And again, you're stretching your brain a little bit because they're both infinite numbers, but you have to work with me here. So what I'm trying to say here is that the top function can approach infinity at a different rate as the bottom function. So let's just say, for example, let's say the top function approached infinity much faster, like orders of magnitude faster than the bottom function. So you'd have a top function on top of this fraction, which is a division. You'd have this top function approaching infinity much faster than this bottom function, which also approaches infinity, but not so fast. So in the end, when you start dividing your numbers out, in the end, when you get to bigger and bigger and bigger numbers, the top function is going to win in that case, and you're going to diverge off to infinity. So in that case, the limit would not exist. You'd go off to infinity. You would diverge to infinity. But look at the other case. What if you had a function where the top function approached infinity much slower than the bottom function? So this bottom function, whatever it is, approaches infinity incredibly fast, like very, very fast. The shape of the plot just goes really, really quickly to infinity, whereas the top one, yeah, it approaches infinity, but maybe not so fast, okay? Well then, when you look at the numbers really far away, when you start to get off close to infinity, you're going to find that the bottom function is going to win, and you're going to have a division of two things where the bottom numbers are always going to be bigger, and it can actually force this thing to zero, okay? So you can actually have a limit that converges to zero in this case if the two things approach infinity at different rates, okay? So I'm giving you a prelude because that's what L'Hopital's theorem is going to do for us. We're going to look at the derivatives of the top and the bottom function, and we're going to see how fast they approach infinity, because that's what a derivative is. It tells you the rate of change of something, how fast something is moving, okay? So we're going to look at the top and the bottom function, how fast they approach infinity, and that's going to tell us if the entire limit is going to exist or not, okay? Okay, so what I'm going to do is I'm going to actually just go ahead and write down L'Hopital's rule, sometimes called L'Hopital's theorem. I call it L'Hopital's rule, okay? And this is how it goes. I'm just going to write it out in all its glory. When evaluating a limit, and this is one of those theorems or rules that every word is important, of indeterminate form and I'll explain what this means in just a second. We've already talked about it. Of indeterminate form of infinity over infinity or 0 over 0, and I've already given you two examples of what those look like, so it shouldn't be a big surprise. Then you evaluate the limit as follows. Okay, evaluate the limit as follows. This is how you're going to evaluate it. You take the limit as x approaches the number a. A could be 0, a could be infinity, a could be 2.947. It doesn't matter, it's just a number. When you're taking the limit of f of x, some function of x, over some other function of x. That's why we denote the top one by f and the bottom one by g, because the top is one function and the bottom is another function. That limit is going to be equal to, as x approaches a, same limit here, and this is where it's going to blow your mind, the derivative of the top function divided by the derivative of the bottom function. That's what the little prime here means. It means take the derivative. So this is very important. Okay, you're going to see this, and some sections in this class I devote more problems to than others because I'm making a judgment to myself what do I think is important and what do I need to stress, and what do the exams stress? There are going to be a lot of problems in this section, and that's because it's asked on all the tests, and there's a lot of different variations, and it's really important because it does help you a lot. I've used L'Hopital's rule a lot, way outside of a calculus class. I've used it a lot, so it's important. So here we go. When you evaluate the limit of indeterminate form, indeterminate just means you get something crazy like infinity over infinity or 0 over 0, and you can't do anything. And the form has to be of infinity over infinity or 0 over 0. We've talked about examples of functions of limits that do look exactly like those. Then all you have to do is take the derivative of the top function with respect to x. Okay, you take the derivative of the bottom function with respect to x, and then you evaluate the limit again. Okay, and a lot of times that'll be enough to go ahead and I'll show you with some examples. That'll be enough right there, and it'll converge, and that'll be the answer. And if you happen to get another limit after you take these derivatives and you still have a form of infinity over infinity or 0 over 0, you just do it again. You take the derivatives again, again and again and again. Eventually, you know how derivatives behave. You end up disappearing functions. I mean, if you have a polynomial, 3x squared, you keep taking derivatives of it, it's going to disappear. So eventually this process is going to end, and you're going to be left with some limit. It's going to be really easy to evaluate. Now notice what you're doing here. When you evaluate this limit of the derivatives, what you're doing is you're looking at how fast these functions change relative to one another. Because that's what the derivative is. It's the rate of change, how fast something changes. That's what it means, okay? So when you take the derivative of the top, you're finding out how fast, what is the rate of change of that guy? How steep is he, okay? And you're doing the same thing to the bottom. And so you're comparing those two functions, and you're seeing how they relate to one another. And if you have one dominant function, then you know, if for instance g of x is dominant on the bottom and he's chasing infinity really, really quickly, then he can drive this whole function off to 0, and we talked about that a little bit before. Okay, so let me go off and show you some other indeterminate forms. Here are some other indeterminate forms. Okay, that you'll see in your problems. You'll see these in your problems, and that's why there's so many different variations in this section. You have the form 0 times infinity. It's a little bit difficult to evaluate that, because if something approaches 0 and something else approaches infinity, which one wins? Does the guy that goes off to infinity win, or does the guy that goes to 0 win? It just depends on the rate of change of these things. Okay, you have a form infinity minus infinity. So yeah, you have an infinite number minus an infinite number, but it all depends on which function is approaching infinity faster to tell you what the actual limit's going to do. You have the form 0 to the power of 0. You have the form infinity to the power of 0. And you have the form 1 to the power of infinity. So these are other forms that you're going to need to understand, because you're going to have problems, and I have problems that deal with these and show you how to do them here in this section. Now, here's the thing. L'Hopital's rule only applies to infinity over infinity form or 0 over 0. And you take the derivative of the top and the derivative of the bottom, and you get the answer. If you have any one of these other forms in your homework problems, you are going to need to beat these things into the shape or into the format of one of these, and then you apply L'Hopital's rule. So if you have an infinity minus infinity or a 0 to the infinity or something, then you must do something to beat it into the proper form, and I'll show you how to do that in these problems here, okay? So, one more thing I want to tell you, and then we're going to dive into some problems. When you take these derivatives here, of the top and the bottom, you're taking the derivative of the top function as a single unit and putting it here, and you're taking the derivative of the bottom function as a single unit and you're putting it here. You are not taking the derivative of the quotient or of the division of these two things, because if you remember, if you're trying to take the derivative of the whole thing from your basic calculus, it's a much more complicated deal. Bottom times derivative of the top minus top times the derivative of the bottom squared, and that's not what we're doing here. So this is really simple. You just take the derivative of the top, the derivative of the bottom, bada boom, bada bing, you take your limit. So what we're going to do, this is the kind of thing that you can put a theorem or a rule on the board and you can talk about it all day, and I can tell you how easy it is and everything else. But really and truly, when you start to see some examples, it becomes clear. So what we're going to do is we're going to do that now. The first problem would be, let's say we're taking the limit as x approaches 2 of the function x minus 2 over x squared minus 4. So the first thing you want to do is find out what form this thing is, and if this limit exists, And if it's an indeterminate form that L'Hopital's rules covers, then we're going to apply it. So if you take 2 and you plug it in here, you're going to get 2 minus 2 is going to be 0. And if you put 2 in here, you're going to get 2 squared is 4, and 4 minus 4 is 0. So you're going to have the form 0 over 0. So you do fall into the realm of what L'Hopital's rule can do for you, and so you can use it. So the next thing you do is you just say limit as x approaches 2, because we're approaching the same limit, and now you just take the derivative of the top. Derivative of x minus 2. Well, the derivative of that's just going to be 1. Okay, that's from your basic calculus. Derivative of that is just 1. And then you take the derivative of the bottom, x squared minus 4. The derivative of that is 2x. Take the 2, bring it out front, x to the 2 minus 1. And there you go, that's from your basic calculus. Derivative of these constants are just 0, so they drop away. Okay. Now you evaluate the limit here. And so here what you're going to have is you're going to have 1 over 2 times 2, because you're approaching 2, so you're going to have 1/4. Okay? So this limit does converge, and it converges to the value of 1/4. So if you were to plot this function on a graph, you would find that it approaches the number 1/4 as x approaches 2. Okay? Even though the top approaches 0 and the bottom approaches 0 individually, you can see how the derivative helps you, because what you're finding out here is that the bottom function here is the driver, and even though they both approach 0, the bottom function is what's causing it to go to 1/4 there. Okay? So you take the derivatives, and what you're doing is you're finding out the rate of change of the top compared to the bottom, and that tells you how the ratio of those two original functions are behaving as a unit. Okay? So what if you had the limit of x approaches -1 of x to the 6th power minus 1 over x to the 4th power minus 1. So the first thing you do is you just plug in your -1 here and see what form you have. Well, you're going to be of the form, what is -1 to the 6th power? It's an even power, so if you take -1 times -1 times -1, on and on 6 times, you will get the number 1. So 1 minus 1 is 0. And on the bottom, you're going to have the same thing. -1 to the 4th power is 1, positive 1, minus 1 is 0. So it's the same form, 0 over 0. Because it's of the special form 0 over 0, I can use L'Hopital's rule, so I'm going to do that. X approaches -1. I take the derivative of the top, which is, from your basic calculus, 6x to the 5th power over 4x to the 3rd power. And that's just your basic derivative of polynomials. These constants drop away. If you have any problems with how I take those derivatives, go back and look at the Calculus 1 DVD. That's pretty elementary derivative taking there. Okay? So you evaluate the limit again. What do you have this time? Well, now you're going to have 6 times -1 to the 5th power. And on the bottom, you're going to have 4 times -1 to the 3rd power. And now these are odd powers, so -1 to the 5th power is -1, so you're going to have -6 on the top, and on the bottom you're going to have -4, and so the answer you're going to get is positive 6/4, which can be reduced to 3/2, right? So positive 3/2, and that's the answer. Okay, so you see it's the same thing. We were approaching -1, and individually the top went to 0 and the bottom went to 0, so we had no idea what to do, but by taking the derivatives, L'Hopital's rule allows us to look at the rate of change of the top compared to the bottom to see how they converge together. So you're looking at how they change together and how one changes relative to another, and that allows you to figure out that it does indeed converge. So these are actually not that hard as long as they fall in the proper form. Okay, what if you have the limit of x approaches 0 of the function e to the x minus 1 over the sine of x? Okay, what form are you going to have here? Well, you're going to have e to the 0, which is going to be 1. Anything to the 0 power is 1. 1 minus 1 is 0. Okay, and on the bottom, you're going to have sine of 0. Sine of 0 is 0. And so you're going to have form 0 over 0. So you're allowed to use L'Hopital's rule here. So all you do is you take the limit to the same place, and you take the derivative of the top. Derivative of the top here, derivative of e to the x is simply e to the x. Derivative of this minus 1 is 0, so it disappears. And on the bottom, derivative of sine x is cosine of x. So you just take the derivative of that, and you evaluate the limit in the same place. E to the 0 power is 1. And cosine of 0, plugging in the 0, cosine of 0 is 1 from your basic trig. And so the answer to this one is going to be 1. And that is the answer there. Okay, so it's the same process. You get a problem, you plug in your limit, you see if you have an indeterminate form that L'Hopital's rule covers, and if it does, you just take the derivative of the top separately from the bottom, evaluate the limit again, and in all of these examples, it's come out so that what we get after we do that first derivative is a number, and that's exactly what you want. It makes life simple. Okay, now the next problem is, what if you have the limit of x approaches infinity of the natural log of x over x. Okay, first thing you want to do is you want to put in infinity and see what kind of form you have. Well, the natural log of infinity, what is that going to be equal to? The natural log of infinity is going to be infinity, and if it helps you here, when you have the natural log of infinity, what you're saying is this is a natural log, so it's base e. E to the power of something is equal to infinity. That's how you read this. E to the power of something is equal to infinity. The only thing that can give you infinity here is if you have an exponent of infinity. So this thing goes off to infinity. And if you were to plot the natural log function, you would see that it bends over, and you would see that as you go off to infinity in x, the natural log does approach infinity. So you have infinity on the top, and of course infinity on the bottom, just because you have x. So this is your form. And from L'Hopital's rule, you can see that you were allowed to use L'Hopital's rule when the form is infinity over infinity. So we're going to do that. Limit as x goes to infinity, and now we just take the derivative of the top. What is the derivative of the natural log function? You remember back to your basic calculus, it's just 1 over x. That's what's on top, and the derivative of the bottom, derivative of x, is just 1. So this thing is going to reduce to the limit as x goes to infinity, okay, of 1 over x, because this is just divided by 1, so it's 1 over x. And then you can see right away that if you put infinity here in the bottom, 1 over infinity is just going to go to 0, because this is going to be 1 over a very, very large number, 1 over 20 million, 1 over 50 million, 1 over 100 billion. Eventually it's going to be 1 over infinity, and this thing is going to reduce to 0. So you can see now that this goes to 0. And this is a good example of what I was talking about before. Here you have a function that approaches infinity, and here you have another function that approaches infinity. But what you have found is that even though the top goes to infinity and the bottom goes to infinity, you would think that that is going to go to infinity some sort of way. What you have found is that the bottom function approaches infinity much faster. Okay? Approaches infinity much faster. So because of that, the bottom gets bigger faster than the top does. And that's why you're taking derivatives here. The bottom gets to infinity faster than the top one. Okay? Because that's what the derivative tells you. So, I mean, you can look here and you can say, well, the derivative of the bottom was 1. It's a constant. So if you go off to infinity, the rate stays the same, but as you look here for the natural log function, the derivative is 1 over x, and as you go off to infinity, the rate of change of this guy gets smaller and smaller and smaller. So the bottom function actually wins, and that's reflected here by this guy right here. And so as you go off to infinity, the whole thing drops to 0. So what you found here is that the bottom function goes to infinity much, much faster, and that drives the fraction to 0. Okay? So what if you had the limit as x goes to infinity of e to the x over x to the third power? Same thing. We want to look and see, well, what form is this? E to the infinity is going to be infinity. Infinity to the third power is still infinity, so here's the form we have. And we can use L'Hopital's rule because we have infinity over infinity, and we do that now. So the limit as x goes to infinity, take the derivative of the top, derivative of e to the x is the indestructible function, e to the x still, and on the bottom, it's 3x squared. That's the derivative of the bottom. And now we say, well, let's plug it in again. Let's put in infinity here. Well, if we put infinity on the top, e to the infinity gives us infinity. And if we look at the bottom, 3 times infinity squared is still going to be infinity. So you might say, wow, I've run into a problem here. I've still got infinity over infinity. Okay, that's a problem. Well, it's just another limit. There's nothing different between this one and the other one other than the fact that they look different, but it's still a perfectly valid limit, so you can still do L'Hopital's rule again. So let's do L'Hopital's rule again. The limit as x goes to infinity, derivative of the top is still e to the x. It's indestructible. It's never going to die. The bottom is 3 times 2 is 6x to the first power, because 2 minus 1. So what form is this? I think you convinced yourself. It's still infinity over infinity. Okay, because e to the infinity is infinity, and 6 times infinity is still infinity. But here I think you'll see that if we apply L'Hopital's rule one more time, the top derivative is still e to the x. The bottom derivative now finally is just 6. We get rid of that x altogether. And so now when we plug it in, the top is going to be e to the infinity is infinity over 6. Okay, so what do you think infinity over 6 is going to be? Well, it's just going to be infinity. Okay, you have an infinite number over 6. And so you have 100 million, trillion, quadrillion on top, and you have 6. So eventually this thing's going to go off to infinity. So this was an example of one where you had a function approaching infinity on the top and a function approaching infinity on the bottom. And what you found by taking the derivatives, which are just the rates of change of these functions, and looking at how they compare, you found that the top function approaches infinity much faster than the bottom one does. And that makes sense. Look, it's an exponential function, e to the x. It's going to go whoop, it's going to go up to infinity much faster than x cubed. If you start plugging numbers in your calculator, you'll see that. And that's just telling you that the top function is going to win, and so it's going to drive the whole thing to infinity. In the previous example, this one, the bottom function went to infinity much faster, and that drives it to 0. So it's kind of cool. You have an example, two examples here. In each case, the top and the bottom approached infinity independently, but you got different answers for the limits because of the way in which they approached infinity. Okay, now let's switch gears a little bit and do a little bit different kind of problem. It's the same sort of thing. We still need to evaluate the limit, but I think you'll see that it's a little bit different. E to the minus x times the natural log of x. That's our limit we need to evaluate. What form is this? That's the first step you should always do when you're looking at evaluating these types of limits like this. Let's plug it in. What we would have is e to the minus infinity times the natural log of infinity. Okay? So e to the negative infinity, I think you can convince yourself is going to be 0. Okay, because e to the negative anything is just 1 over e to the infinity. That's sort of how you would rewrite that in your head. So you'd have 1 over infinity, which is going to give you 0 for that whole thing there. And natural log of infinity, we talked about before, that's going to give you infinity, because when you take the natural log, if you look at the natural log function, it approaches infinity as you go off to infinity. So that's infinity. So here's the form. It's 0 times infinity, and if you look back at L'Hopital's rule, you can only do it if it's the ratio of infinity over infinity or 0 over 0. Anything else, like any of these other indeterminate forms, this is the one that we have, any of these other ones, you must beat it into shape to put it into the shape in order to actually use L'Hopital's rule. So we're going to do that. We're going to beat it into shape. In this case, there's not much beating involved. It's pretty easy. All you have to do is take this and write it like this. You can write it as the natural log of x on the top over e to the x on the bottom. Now notice we've changed nothing. All we've done is we've moved this exponential down below, because it's a negative exponent. We can do that, make it positive, okay? And now what form do we have? Putting infinity here, we have infinity in the top, and e to the infinity is infinity on the bottom. So we've put it in the form of what we can use L'Hopital's rule for. Okay, so we've done that, and now we can just use L'Hopital's rule. There's nothing magical about it, so let's go ahead and start taking derivatives. X goes to infinity. The natural log of the derivative of the natural log is 1 over x, and the natural log of e to the x, the derivative of that, the derivative of e to the x is simply e to the x, and so what you're going to have here is, if you evaluate this, is you're going to have 1 over x times e to the x, just moving this down into the denominator here. And so what you're going to have is 1 over infinity times e to the infinity. Okay, so you're going to have infinities all around, so you're going to have 1 over infinity, which is going to equal 0. Okay, so all you did was you took this, put it downstairs, and put it into the form of L'Hopital's rule. Then you can do the derivative of the top, derivative of the bottom. And from here on out, I was just messing around with it to plug in the infinity here. Okay, now the next problem is, what if I had the limit as x goes to pi of the function x minus pi times the cotangent of x? Okay, the first thing to do is figure out what form is this. Okay, what form is this? Well, If I put in pi here, I'm going to have pi minus pi, so I'm going to have 0, but what does this result in? Well, cotangent, if you remember, is simply cosine of x over the sine of x. And if you want to go ahead and plug in pi here, you can just put cosine of pi over sine of pi, because that's what we're plugging in. We want to see what form it is. Cosine of pi is -1. I think you can convince yourself. And sine of pi is 0. So that's just going to be infinity. So the form is 0 times infinity, because pi minus pi is 0, and then this evaluated to infinity, so it's going to be 0 times infinity. So you can't use L'Hopital's rule straight out of the gate. You must do something to it. So what we're going to do, is we're going to move this cotangent down below. That's kind of what we've done before, so we're going to do this here and see if that helps. We're going to have x minus pi here, and we're going to move the cotangent down below, but in order to do that, we have to write it as 1 over cotangent. You see, this is the same exact thing. If I were presenting this to you, I would say, well, if this is the case, how do you simplify it? You would take this, you would, since it's dividing a fraction by a fraction, you would flip it over and multiply, so it would be this times cotangent. So these two things are exactly the same. I moved it to the bottom, but I had to make it an inverse to make it the same quantity. Okay? Now, why in the heck would I do that? I'm doing that because 1 over cotangent is equal to x goes to pi of x minus pi. 1 over cotangent is the tangent. Okay? And you can remember that from your rainbow that I taught you. Sine, cosine, tangent, cotangent, secant, cosecant. Cotangent is 1 over tangent. That's what the rainbow means there. So I moved the cotangent down and made him a reciprocal to make it algebraically correct, and then I turned him into a tangent function. Okay, now let's check our form. What form do we have now? On the top, it's still going to be 0 because pi minus pi is 0. And on the bottom, it's going to be sine of pi over cosine of pi. So it's going to be form of 0 over sine of pi is 0 over cosine pi is -1. This thing goes to 0, so it's going to be 0 over 0. So the form is 0 over 0, which is legal to use L'Hopital's rule. So after we've done all of that, we just do it. Limit as x goes to pi. Now, what is the derivative of the top? X minus pi, take the derivative, is just going to be 1. Derivative of this constant number pi is going to be 0. Derivative of tangent is secant squared of x. Okay, secant squared of x. And I can rewrite this as the limit as x goes to pi of 1 over secant x squared. I've done nothing here, but I've just written the whole thing as a square because 1 squared is 1 and secant squared is secant squared, so I've done really nothing there. The reason I did that is because I want to use my rainbow again: sine, cosine, tangent, cotangent, secant, cosecant. Secant is 1 over cosine. Okay, so I can rewrite this again just to make it easy. The limit as x goes to pi of what? Cosine squared x, because I've turned this 1 over secant into a cosine, cosine squared. So now it's something I can do. So this is going to be the limit. Well, actually, I don't even need to write the limit anymore, because now this reduces down to cosine of pi squared, which is going to be -1, because cosine of pi over here is going to be -1 squared, which is going to give you +1. +1 is the answer. Okay? So, looks complicated, but it really isn't, because all you have to do is find the form of it. When you have a form 0 times infinity here in your limit, it's pretty much almost a guarantee that you're going to want to take one of these and move it to the bottom, even if you have to make him a reciprocal to make him algebraically correct. And in this case, we turned him into a tangent, and then we had the proper form. 0 over 0. We did L'Hopital's rule, turned him into a secant squared, and we turned him into a cosine squared, so that we could then do our magic with the trig, and we had -1 squared, which came to be a +1. So there is a method to the madness. It's just that when you get to the indeterminate forms, you just have to play with it, and you're going to get some practice. I mean, none of us are born knowing how to do this. I mean, once you see it enough times, you'll get the hang of it. When you see 0 times infinity, chances are you're going to have to put one of them on the bottom. Now let's do one that we haven't done before. What if we have the limit as x goes to 0 of 1 over x to the 4th power minus 1 over x squared? Okay, what form do we have here? I think it's pretty easy for you to see. 1 over 0 to the fourth is infinity. 1 over 0 is infinity. You may have learned a long time ago that that was undefined, but something divided by nothing goes an infinite number of times. And you have minus 1 over 0 squared is going to be 0, so you're going to have infinity. You have infinity minus infinity. And that is one of these indeterminate forms that we said you could run into that you would have to beat into the shape of this for L'Hopital's rule. So what we're going to do is we're going to rewrite this thing, and we're going to try to get a common denominator and see if we can make some progress. What we want to do is, this is the difference of two fractions here. So what we want to do is we want to see if we can find a common denominator. And we're going to do that by, I'm going to multiply this fraction by x squared over x squared. I've multiplied by 1. I haven't changed anything. I've just multiplied by 1. The reason I'm doing it is because I want to multiply these on the bottom and get an x to the fourth power so I can actually combine these terms together and see what I have. So when I do that, the limit as x goes to 0 of 1 over x to the fourth power minus, now let's do this multiplication, x squared over x to the fourth power. Okay, now you can see why I did that, because the limit as x goes to 0 of 1 minus x squared over x to the fourth. Now I've combined them. I've just subtracted those fractions together. Common denominator stays the same. I've subtracted the tops. Now, what form do we have? Okay, now let's continue on and let's see what we have here. Let's say we go ahead and plug in 0 here. What you would have is 1 minus 0 squared on the top, and on the bottom you'd have 0 to the fourth power. So on the top you would have simply 1 because 0 squared is 0, and on the bottom you'd have 0. So you have 1 over 0. Anything over in 0 goes to infinity times, and so the answer to this limit is infinity. So this time we really didn't have to do L'Hopital's rule. We didn't have to actually take derivatives of anything. What happened was you had a function that went to infinity and another function that went to infinity, and when you combine them together into one fraction, you were able to find that as a sum total, the thing also went off to infinity, and you found that out because when you combined them out, you were no longer in an indeterminate form. Indeterminate form just means that you have 0 over infinity or 0 over 0. You have infinity over infinity or 0 over 0 or any other of these indeterminate forms. It means you can't evaluate it. But when you get down to a point where you have 1 divided by 0, you know this is going to go to infinity because anything divided by 0 is infinity. Okay, is infinity. Now let's do another one of the form infinity minus infinity that's a little more challenging. Okay, here's another problem here that's going to be a little bit similar, but also quite a bit different. So you have the limit as x approaches 0 of 1 over x minus cosecant of x, and if you wanted to find out what form this is, you'd put in 0 here, and you'd have 1 over 0, which is infinity, and then you'd have the cosecant of 0, and don't forget the cosecant is 1 over the sine, and you can find that out from your rainbow. Sine, cosine, tangent, cotangent, secant, cosecant is 1 over sine. So you have infinity minus the sine minus 1 over the sine of 0. So what is this? Infinity minus 1 over sine of 0 is what? Sine of 0 is 0. So the form you have is infinity minus infinity. 1 over 0 gives you infinity. So you're in one of these indeterminate forms. It's the first step, but it is not an indeterminate form. You can just use L'Hopital's rule 4 right away. So you want to beat it into shape. You want to beat it into shape. Okay, the first thing to do here is I want to change my cosecant into my 1 over sine, and I want to try to find a common denominator here, just like we did before. So you see there's a pattern. When you have infinity minus infinity, you want to see if you can find a common denominator and see if that gets you anywhere. So let's do that. Limit of x goes to 0 of 1 over x minus, and I'm going to change this cosecant into 1 over sine of x. We just did that. And that's just a definition. Cosecant is 1 over sine of x. And now I want to find a common denominator here. So how would I do that? When you have a common denominator you want to find and nothing is really common between them, you just start multiplying. Limit as x goes to 0 of 1 over x, and I'm going to multiply this fraction by sine of x over sine of x. I have changed nothing. I've multiplied by 1. Okay, and then the other fraction, which is 1 over sine of x, I'm going to multiply that one by x over x. Again, multiplying by 1, I haven't changed anything. So the first fraction you multiply by sine over sine, and the second fraction you multiply by x over x. Now why in the heck would I do this? The reason is because what I'm going to have is the limit as x goes to 0, okay, of sine of x over x times sine of x minus x over x sine of x. I've got my common denominator. That's the reason why I did that. And so when you do this, limit of, just go ahead and subtract your fraction, sine of x minus x over x times sine of x. Now let's see if doing this did anything for us. Let's figure out what form we're in now, okay? If we plug in 0, what we're going to have is sine of 0 minus 0 over 0 times sine of 0. What form does this do? Sine of 0 is 0, so you're going to have 0 minus 0 on the top, and on the bottom you're going to have 0 times sine of 0, which is 0. So you have zeros all around, 0 over 0. Look at that. You finally have a form that you can use L'Hopital's rule for. Because what you've done is, you see, you've done nothing here other than do very legal algebra to get this thing into a form so that it is now in the form of 0 over 0, which is the form you need to go off and do L'Hopital's rule. Okay, so now that you're to that point, what you have to do is actually do L'Hopital's rule. Take the derivative of the top, derivative of the bottom. These aren't going to be very hard derivatives, so let's do it. Limit as x goes to 0. What's the derivative of the top? Derivative of sine is cosine x minus derivative of x is 1. And the bottom's a little bit tricky because you have x times sine of x, so you have to use your product rule. So it'll be x times the derivative of sine, which is cosine of x, plus sine of x times derivative of this guy, which is 1. So this times the derivative of this plus this times the derivative of that, okay? So we still haven't done the limit yet. Let's go ahead and simplify. Cosine x minus 1. Actually, there's not going to be too much simplification to do here. X times cosine of x plus sine of x. Now let's see what we have here. Let's go ahead and plug in 0 and see what we have. What we're going to have is cosine of 0 minus 1 on the top, just plugging in for 0 here, x is equal to 0. On the bottom, you're going to have 0 times cosine of 0 plus sine of 0. And let's just do this and hope that we got something simpler. Okay? Cosine of 0 is 1, so you're going to have 1 minus 1 on the top. And on the bottom, you're going to have 0 times cosine 0. Cosine 0 is 1, so you're going to have 0 plus sine of 0 is 0. So you're going to have 0 over 0. Okay, so what have we found here? We have found that after we did L'Hopital's rule one time, we still ended up with a form of 0 over 0. So just like the simpler problems, if you get to the point where you're making progress, but you still have a form that L'Hopital's rule falls into, you just go ahead and do it again. And hopefully by taking derivatives, you'll make the thing simpler to the point where you will not have an indeterminate form. So we're on the right track. Let's do it again. We're going to use this guy as our starting point. We're going to continue taking derivatives and see what we get. Limit as x goes to 0. What is the derivative of the top? Derivative of cosine is negative sine of x, and this minus 1 is going to disappear when you take the derivative. Derivative of a constant is 0. On the bottom, you're going to have something fairly complicated. The derivative of this is going to be that product rule. This times derivative of this plus this times the derivative of that. So you're going to have x times derivative of cosine is negative sine of x plus this times derivative of this plus this cosine of x times the derivative of x, which is 1. Okay, don't forget plus, you still have this. Derivative of sine is cosine of x. And you can see you're getting things a little bit simpler here. You've already dropped out this x here. Let's see if it gets simpler. You're going to have limit as x goes to 0 of negative sine of x over, let's go ahead and simplify it here. We're going to have negative x times sine of x right here plus 2 times cosine of x. This plus this gives me 2 times cosine of x. Now let's go ahead and plug it in and let's see if we get an indeterminate form, or let's see if we get something simpler out. Plugging in x is equal to 0, you have negative sine of 0, and on the bottom you'll have negative 0 times sine of 0, just plugging in right here, plus 2 times cosine of 0. Here, now let's see what we get. On the top, sine of 0 is 0, so you'll have negative 0. Now there really is no such thing as negative 0. I'm just carrying the negative along just for grins at this point, okay? So you have negative 0, and on the bottom you'll have 0 times sine of 0, which is also 0. So again, you'll have negative 0, and again, I'm carrying it along for grins at this point, plus 2 times cosine 0. Cosine 0 is 1, so you'll have 2. Finally, we do not have an indeterminate form. What you have on the top is 0 over 0 plus 2. So you're going to have a big fat 0 here because you have 0 divided by a number, and that's going to drive the whole thing to 0. Okay, so here's the thing. It looks complicated and there's a lot of stuff on the board, but really it's methodical. You have a function, you plug in, and you found that you had the form infinity minus infinity. When that happens, you probably want to try to combine those into one term and see what you get. We changed this cosecant into a sine because we wanted it into a fractional form so that we could combine it. And then in order to do that, we just had to find common denominator. So we multiplied each fraction by something so that we could find a common denominator. We put this thing together, and then when we did that, we did L'Hopital's rule on the top. We took the derivative of the bottom, we reduced it to this, and we plugged it all in there. We still had a form that was indeterminate, 0 over 0. So we knew we wanted to try it again. So we took the derivative of the top, we took the derivative of the bottom, we plugged in 0 again, and we got something that's not indeterminate. We had a 0 over a number. 0 divided by anything is 0. So that one actually does converge. Okay, now the next problem is going to be of a different type of indeterminate form, and you're going to need to pay attention here because you're going to have problems like this. And it can seem a little bit tricky, but I'm going to hope to make it easy for you. X to the 1 over natural log of x. X to the 1 over natural log of x. So this 1 over natural log is all up in the exponent up here. So what form would this be? Plugging in 0, the form is going to be 0 to 1 over natural log of 0. Okay, what is natural log of 0? Natural log of 0 is, think about it, natural log of 0 is e to the some number is 0. Well, what number could that be? It's got to be negative infinity. Okay, so what you're going to have here is the form is going to be 0 to the 1 over negative infinity, which is going to be 0 to the power of 0. Okay, because 1 over infinity is going to give you the 0 up there, so you have 0 to the power of 0. And if you look over here, 0 to the power of 0 is one of those indeterminate forms that you can't do without using L'Hopital's rule. Okay, so we want to use L'Hopital's rule. But here's the thing. When you have the form of an exponent like this, something raised to the power of something, and you have the form 0 raised to the power of 0, or a lot of times infinity raised to the power of 0, a lot of times you're going to have to do a natural logarithm trick. So I'm going to go through the example. You're not probably going to understand why we're doing it this way until we get to the end. And then when we get to the end, it'll be like, oh yeah, that makes total sense why we did that. So let's do it. What we want to do, I'm going to write the word here, try, down, just to remind you that we're trying something out, and I'll show you in the end that it actually works. We're going to try to take the limit of something related to this, but not quite. Because remember, this indeterminate form we can't do until we get it into a different form. Okay, so what we're going to try to do is we're going to try to take the limit of the natural log of our original function, 1 over natural log of x. So you see, think about that. The original function was this. We were taking the limit. Now I'm going to wrap the whole thing in a natural log. Okay, and now we're going to take the limit of that beast, and I'm going to show you at the end that that's useful. Now remember back to your knowledge of natural logs back in wherever you learned it, trig or algebra or whatever. When you have the natural log of something raised to something else, that can be written like this: 1 over natural log of x times natural log of x. What you do is you take this exponent. When you have the natural log of something raised to a power, you can take the exponent out, stick it in front of the natural log like I've done here. This whole thing comes out in front, and then it's natural log of what's left over. That is something that if you don't remember, you probably need to go off and review, because we're going to be doing it quite a bit. Okay, we're going to be doing it quite a bit. So because we wrote it like this and because we wrote it like this, you can see that this results in the limit as x goes to 0 of natural log of x over natural log of x. Okay, and that results in the limit as x goes to 0 of the number 1. This divided by this just gives you 1, and then you take the limit of a constant, you're just going to get 1 back. Okay, so you get the number 1 back. That's the answer. But think about this. It is the answer to this limit, which is not our original problem. See, I took the original thing, I stuck a natural log on the outside, and I said, look, we're going to evaluate this, and I'm going to show you later why it's useful. Okay, let me show you now why it's useful. We have found that this limit does exist. This limit does exist. Okay, we need to figure out how that helps us find our original limit. Okay, so think about this. You know that the power of e to something is exactly the opposite of the natural log. So if I take e to the natural log of x, I'm going to get x back. These are opposites. Natural log is base e. So e to the natural log of x is just x. And likewise, a natural log of e to the x also gives you x, because they're opposites of one another. Base e to the power of x is going to give you what's left back over here. So that's a useful thing. What I really want you to focus on is this, and make sure you understand that. E raised to the power of a natural log of some number, 1, 2, 3, 4, 10, whatever this number is, if you take e and raise it to the natural log of this number, you get back the original number. Okay, so here's the crucial thing you have to think of. Here's the crucial thing you have to think of to make this leap, and then these problems will seem easy. When you have the form 0 raised to the power of 0, and what we did is to solve it, we haven't even finished yet, is we take the natural log of the whole thing and find that limit, which I've shown you how to do. Then you can write down on your paper the original limit is equal to e to the 1 right here, which is just going to be equal to e. Now I'm going to let that percolate for a second and let me tell you why. Because if I were to rewrite my original limit as limit of x goes to 0 of e to the natural log of x to the 1 over natural log of x, okay, then what I get out of this is my original function, x to the 1 over natural log of x. Now I want to spend some time to talk about this because it doesn't seem obvious at first. What you did is you knew you had a function you wanted to find the limit of. Okay? You wrapped it up in a natural log, knowing full well that if you raise the answer you get to the power of e, that's the answer to the limit that you actually were seeking. Okay? You found the limit of something else. Okay? And another way to think about it is, if you were to write the original problem as x goes to 0 of e raised to the power of what you wrote here, then what I'm finding is the limit of the original function, because these two things kind of cancel. So it's kind of a goofy way to write it, but if I would have written, if the problem would have said in the beginning, find the limit of e to the natural log of this stuff, then you would have known, because you're a smart person, that these two things kind of cancel, and what you're really finding the limit of is this thing. Okay? So all I did is shortcut a step, and I said, well, let's find the limit of this. That's exactly what we found the limit. Let's find the limit of this, which I showed you how to find right here, 1. And then at the end of the day, we'll just take e and raise it to that power, and that is going to be the limit of the original function we wanted. That's a mouthful. Make sure you understand that. Rewind the tape and listen to it again if you have to. But what you're doing is you're wrapping it in a logarithm, you're finding the answer, and you're raising the answer to the power of e, because that is the limit of the original function. E to the natural log of the function is the function. Okay, we're going to do one more of this type, and we're going to make it that much clearer. Okay, now here's a problem that's going to be kind of lengthy. Let's say you have the limit as x goes to 0 of 1 minus 2x to the 1 over x power. Okay? 1 minus 2x to the 1 over x power, what form would this be? Okay, put in 0 here. We're going to have 1 minus 2 times 0 is 0, all raised to the 1 over 0 power. Okay, so you're going to have 1 raised to the power of infinity. And that, look down here, is one of our forms, 1 raised to the power of infinity. Now, anytime you have 0 to the 0, infinity to the 0, or 1 to the infinity, you're pretty much going to have to use this natural log trick I told you. Okay? which is what we're going to do here. What we're going to do is we're going to wrap this thing in a logarithm. We're going to see if we can find the limit, and then once we can find the limit, we are going to then raise the answer to the power of e, and that's going to be the answer to the original limit, because e and logarithms are opposites of one another. Okay, so we're going to find the limit as x goes to 0 of the natural log of 1 minus 2x, let me put a bracket here, 1 minus 2x to the 1 over x. Okay? Now we're going to do this, see, this is why the natural log thing is useful, because when you take the natural log of something raised to a power, you just write it as 1 over x, take this out in front of the log, times the natural log of what's left over, 1 minus 2x. That comes from algebra. Okay? And I kind of forgot to write that this is still a limit as x goes to 0. Okay? So you have 1 over x times the natural log of 1 minus 2x. Okay? So what you want to do is see what kind of form you're dealing with here. What form would this be? Looking at the first part, you're going to have 1 over 0 times the natural log of 1 minus 0, putting in 0 here. So what you're going to have is 1 over 0 is infinity times natural log of 1. And what is natural log of 1? It's e to the power of something is equal to 1. And the only thing that fits in here to make this thing 1 is 0. E to the 0 power is 1. So the form that you're dealing with, since natural log of 1 is 0, then the form that you're dealing with is infinity times 0. Okay? And we've already dealt with this. We've already dealt with that. Remember when we had infinity times 0, what we did was we moved one on top of the other. So let's try to do that. Let's try to do that. Let's rewrite it like this. Let's say you have natural log. We're going to take the limit as x goes to 0, and we're going to have the natural log on the top of 1 minus 2x over x. All we did was write this as a fraction on the top. Okay? All right. So now, what form do we have now? Let's see if we can use L'Hopital's rule. On the top, 0 plugged into here, 1 minus 0 is 1, natural log of 1, we already said this just a minute ago, natural log of 1 is 0. Okay? And on the bottom, you're going to have 0. So now you're in the form of what you can use L'Hopital's rule for. So you go ahead and apply L'Hopital's rule. Okay, this is what we talked about, beating it into shape. So let's take the derivative of the top. The limit, as x goes to 0, derivative of the top, derivative of the natural log is going to be 1 over 1 minus 2x times the derivative of the inside, which is negative 2. Okay, so we take 1 over the argument, that's our derivative, times derivative of the inside, which is negative 2. Derivative of the bottom is just 1. So this is limit as x goes to 0. The top and the bottom is just divided by 1, so it's just going to disappear. So this is going to be negative 2 over 1 minus 2x. Okay, now let's plug it in and see what we get. We get negative 2 over 1 minus 2 times 0. So we have negative 2 over 1 minus 2 times 0 is 0, so you're going to have 1 on the bottom. So the answer is negative 2. So you converge to a number and you converge to negative 2. But don't forget that you have solved the limit of this limit right here, which has a natural log wrapped around it. That is not the original limit you wanted to find. So all you have to do when you do this natural log trick is then say, okay, well the real answer then is e to the negative 2. You just raise the answer to the power of e to the power of your answer, and that's going to be it. Because what you're doing here is you're saying, you found the limit of the natural log of this thing, and if I had taken the original function and raised e to the power of all of this stuff right here, I would be finding the limit of what's inside here. So instead of carrying that through the whole problem, I just found the limit of this and then said e to the power of this gives me the answer. Okay, so in this problem, what we did is we had this guy, we had the form of 1 to the power of infinity. Anytime you have a 0 to the 0 or infinity to the 0 or 1 to the infinity, you're probably going to have to use this natural log trick. Wrap it in a natural log, take the exponent out in front of the natural log, and then we put it into this form, which is really just simply combining these two things, putting the natural log on top. This was a form of 0 over 0, which we could use L'Hopital's rule for. Take the derivative of the top, the derivative of the bottom, and you have this function here that's left over. You plug in 0, and you get an answer. And then you just take your answer, say e to that answer, and that's how you do this problem. So This section was a lengthy section. We covered L'Hopital's rule. I covered it in a fair amount of detail with a lot of different problems because you actually use L'Hopital's rule a lot. When you go on, most of you guys taking Calculus 2 are going on into engineering or physics or chemistry or some science. You're going to be doing problems where you're looking at the rates of changes of things, and a lot of times you run into this thing where the top goes off to infinity and the bottom goes off to infinity and you can't do the limit. You don't want to whip out a computer and plot it, so what does it look like? L'Hopital's rule, use it all the time. So you have, you can use L'Hopital's rule if you have the form 0 over 0 or infinity over infinity. And if you have a different indeterminate form as given on the board over there, you have to massage the problem into the shape and into the form of what you need to apply L'Hopital's rule. And once you do that, you take your derivative of the top, derivative of the bottom, evaluate your limit, and that will be the way to do these types of problems.